So we have 3 more tests to learn, and one of them is this. So far in all of the previous sections we've talked about, we had the section 11.2. I'm just going to make a quick little list. We will summarize this, so you can write this down or not. We had the test for divergence. We had, this is section 11.2, test for divergence. We had geometric series, and we had telescoping series, right? And for those last 2, you could actually find the exact sum. Do you know what I mean by that? You could actually figure out what the series added up to. Okay, in section 11.3, we shifted a little bit away from figuring out what a series converges to just looking at does a series converge or diverge, and for that we used the, what was the test in section 11.3? Integral test. And that required that your function f of x be positive, continuous, and decreasing, right? Those 3 things. The thing I want to focus on now is it had to be positive, which means the terms of your series had to be positive. Does that make sense? Okay. In section 11.4, we had 2 kinds of comparison tests, right? The direct comparison test and for just limit comparison test, which I'll just call LCT, just abbreviate it that way. Both of those required just one thing about your terms, and it was that they be positive, right? So far, pretty much nothing has let us deal with things that have negative terms. Does that make sense? With the small exception of some geometric series could have negative terms, and so could some telescoping series, right? But the 2 tests we learned, well, the 3 tests, the integral test, the comparison test, and limit comparison test, you have to have positive terms to apply them. So today, we're going to learn about how to deal with a specific kind of series that does actually have negative terms, and it's called an alternating series. So an alternating series is a series whose terms flip-flop positive, negative. And the flip-flopping has to happen in a very specific way. It has to either go plus minus and then pattern repeats, or it has to go minus plus. It doesn't matter which one comes first, but the pattern has to flip-flop every other term. So like for this first one, I just want you to list out the first few things in the sum. Like when I plug in 1, what is negative 1 to that power that I get when I plug in 1, a positive or negative result? When I plug in negative 1, it's negative 1 to the, when I plug in 1, it's negative 1 to the 0, which makes 1. So the first term is 1 over 1, right? Does that make sense? When you plug in 2, you get negative 1 to the first over 2. So that would be minus a half. Does that make sense? What's the next term going to be? Positive or negative? I just told you it was positive. Plus 1/3, and then it would be minus 1/4, plus a fifth, etc., right? But do you see that what's happening is that the terms alternate positive, negative? Okay. This one, if I plug in 1, is my first term positive or negative?
Negative.
Negative, yep, so that'd be negative 1 over 2. Next term is positive, which is, I think it's 2 over 3. Do you guys agree? What's going to come next? Minus 3 over 4, etc. So it doesn't matter if the first term is positive or the first term is negative, but what does matter is that there's flip-flopping after that first term. Okay, that's what it means to alternate. And I think I didn't put this on my sheet, but it's on yours. A sum like 1 plus 1 minus 1 minus 1 plus 2 plus 2 minus 2 minus 2, etc. That is not alternating. Do you see what I mean? It doesn't flip-flop every other.
It's also just telescoping, right?
It is telescoping in some sense, yes, but it's not alternating.
Right.
Alternating means flip-flops every other.
Does some not be 0 because infinity minus infinity doesn't necessarily...
I'm not prepared to talk about that one. My point was just that it's not alternating, okay?
Okay.
All right, so here is the alternating series test. So what you do is you separate out your series into the flip-flopping bit, which often is a negative 1 to the n, and then the other part. Does that idea make sense? You got the negative 1 part and the other part that has n's in it. And you call the part that is positive like b sub n, just give it a name. And if two things happen, the series is convergent. If the limit of those b sub n's is 0, and if b sub n plus 1 is less than b sub n. What is this thing saying about the b sub n as a sequence? So b sub n is decreasing.
So this isn't like previously that if it was decreasing after 2,
It's also the same kind of idea like before, yep. So, and it's a great point. Showing this is the same as showing the terms for an integral test are decreasing, as in the same sort of rules apply. You can say something is obviously decreasing if you only have stuff in the bottom. And otherwise, how would you show something was decreasing? You'd use a derivative. So the same sort of stuff as applies for 11.3 applies for this. Yes?
So this is for all n, does that mean that there can never be a spot in the entire sequence where it's increasing?
No, I think that this really is a bit too harsh. For all n bigger than some capital N. So if your sequence starts to decrease like after n equals 10, you could just add the first 10 things of the series and then consider the series from like that point on and apply the integral test to it. So it's the same as the alternating series test. Sorry, I said the wrong thing. It's the same kind of condition as the integral test. As long as it happens eventually, it's good enough. But in proving it, it's a little bit easier to just be a little bit strict about it because that's going to make the proof a little bit easier to look at. Does that idea make sense? Yeah. But same stuff as for the integral test. Okay, so how I'm going to prove this is I'm going to draw a picture, and then hopefully the picture will make sense. So here's my picture. So let's start with, we have the sum n equals 1 to infinity, negative 1 to the n minus 1, b to the n. And I want to show if those two things happen, if the limit of the terms is 0, and if the b sub n's are decreasing, then your series converges. Okay, so let's write down the partial sums, just a few of them. S1 is adding up the first thing. Because of the way this series is defined, is my first thing positive or negative? Positive. Okay. Oops, that should say S1 equals B sub what? 1. Okay. And then S2 will equal B1 minus B2. S3 would be B1 minus B2
Plus B3.
plus B3. And we'll list S4, I promise I have a picture. S4 would be B1 minus B2 plus B3 minus B4. You guys get the idea? Okay. Okay. So you have 0. I'm going to color code this the same way that Jill did. So first we have S1 equals B1. So you've assumed you've taken all the negative stuff out of the B's and the B's are just positive. So when you plot S1, you go over here to some place. S1 equals B1 at some positive number.
A negative number to the power of 0 is positive 1, right?
Yes.
Okay.
Yep, exactly. Anything to the power of 0 is positive 1 except for 0.
What's 0 to the power of 0?
Undefined. It's actually, you did stuff like that in section 4.4 of Calc 1. You found limits like that using L'Hopital's rule and natural logs. It was one of those indeterminate forms. So it's not, I mean, I can tell you, like, if I have time in a class, I can go back to that, but yeah, that's technically not defined. Okay. Now, the next partial sum, when you go backwards, how do you know, I'll draw this and tell me how do I know that I'm right? How do I know I can't go all the way back to 0? Why is that the case?
Because it's
Because the b sub n's are decreasing, which means that b sub 2 is less than b sub 1. Does that make sense? So that's where your partial sum S sub 2 falls. It has to be bigger than 0. And that's because the requirement that B2 is less than B1. So their difference is some positive thing, right? Okay. Now what happens when I add on that B sub 3? Like I'm here, can I go all the way back to S1? And you have to kind of end up at just a hair shy. And that's where your third partial sum is going to end up.
Is it convergent on some value on this?
Yes, exactly. What happens to the next one? You go backwards, but can you go all the way back to purple?
Nope.
Nope, not all the way. So you go backwards to something. There's S4. Does that make sense? And without doing any official plotting, S5 is going to be smaller than S3, right? And S6 is going to be bigger than S4, right? So, and there's your sum S, someplace in the middle. It doesn't have to be like halfway in between, but somewhere in between those things. And the basic idea here is that the limit as n goes to infinity of S2n, sorry, I wrote the wrong thing, S2n, has to be equal to some number S. And that's because this sequence, S2, S4, etc., is increasing, and bounded above. Does that idea make sense? Yes.
I don't know what you mean by S2.
Oh, good question.
What do you mean multiplying by 2?
Yes, and what the 2 does to that, so Sn is the sequence of partial sums, you get that, right? When I do S2n, that means I'm looking at the even parts of the partial sum. It's like when I plug in 1, I get S2, when I plug in 2, I get S4. That's what it means, but that's good to ask because somebody else probably was also confused. So this looks at the evens only.
That's only the positive or negative parts of the,
Say that one more time.
that's only the positive or the negative parts of the infinite sum.
That is true. That is only the positive or negative parts of the infinite sum, depending upon if your first term was negative or positive.
Yeah.
Is that right? I'm not sure if that's completely correct because in those parts, in those partial sums, you have the sum of the first few things up to that point. So I don't think that's right. Okay? What this is just saying is add the first 2 terms, add the first 4 terms. That's all.
Oh, okay.
Okay? But do you agree that if I just look at like the S2, the S4, the S6, that those things are kind of going up? You buy that from the picture? And also they're bounded because, well, anyhow, something, this S1 is above them, anything's above them, so they have to converge by that monotonic sequence thing. That's the technical reason. Okay. Now here's the last bit. What you have to also show is that the odd things converge to the same number. It's a little bit technical, but you assume that this thing converges so it goes to something S. We don't know what S is, but we're going to show the odd ones go the same place. So the limit as n goes to infinity of S sub 2n plus 1. And that 2n plus 1 means you're getting all the odd numbers. Like when you plug in 0, what's 2 times 0 plus 1? When you plug in 2, 2 times 2 plus... When you plug in 0, you get 1. Plug in 1, you get 3. When you plug in 2, you get 5. That gets all the odds. This is the same thing as taking S2n and adding the next term. As in, the way to get S5 is the same thing as S4 plus the fifth term, right? Or minus, depending upon it. And then you can break this limit into two things. And then where does this guy go by assumption? Mm-hmm. So that thing also equals S. I mean, it's quite technical.
Do I have to do that every time?
No. You can just use it now. But the point is that there were two things you had to check. One thing was that the limit of the terms goes to 0, and that's used in this step to prove that the even partial sums and the odd partial sums go the same place. And the other thing that you assumed is that the stuff was decreasing, right, this little bit there. And that decreasing made these things increase to S or decrease to S. Like, that's what it did. But once you show, so this is kind of why it works, but all you have to show to use this test is check that these two things are met, and if those two things are met, the series converges by this test. And that's the reason why. But the picture to have in your head is good, a picture of the partial sums either march up to S or march down to S. And that part's conceptually, I think, not super, super hard. The technicalities of this bit are just gross. So we'll just like ignore them for a bit now. Yes? Mm-hmm. You're making a confused face at it. This thing goes to 0 by assumption. Is that what you're confused about, Natalie? Okay, and it's because if you look at the very top in the box, it says limit as n goes to infinity, bn equals 0. So you assumed that happened so that I could make that step in the first place. If I hadn't assumed that happened, I couldn't make this step. Okay, so let's actually use this to show some stuff converges or diverges. So how about this series? Is it convergent or divergent? So first of all, I think the first thing you should say is verify that the series alternate. And then tell me what B sub n is. Like, that's my sort of first step you should make, first instruction. Okay, so is your series alternating? Is it pretty obvious? Yeah, whenever you have a -1 to the n, the flip-flopping happens. Just tell me you've checked that, okay? So the series is alternating. With B sub n equal to what? 1 over n. Okay, then step 2, check the alternating series test, which I'm going to call AST because, like, ain't nobody want to write that every single time. So check the AST, I want to say conditions. Limit as n goes to infinity of Bn is the limit as n goes to infinity of 1 over n, which is 0. You don't have to say that first part, I'm just saying that to be extra thorough in class. And in this one, is it pretty obvious that Bn plus 1 is less than Bn? What's Bn plus 1? In other words, you plug n plus 1 into this. 1 over n plus 1. How does that relate to Bn, which is 1 over n, who's obviously bigger? The one on the right side, correct? So the B sub n is decreasing. So by the alternating series test, the series does what? Converges. So doing the AST involves kind of checking three things, making sure you alternate and then checking that those two conditions are met. And if they're both met, great. If they're not met, boo, test fail.
When does the regular 1/n diverges and this one converges?
That's a great point. I was just going to say that. Do you guys understand his question? If you took that negative out of the top and made it 1/n instead, that diverges, right? But when you add in that flip-flopping, it doesn't. And that's a special kind of convergence called conditional convergence, which is in section 11.6, which is like the next section we're going to talk about. But the reason that this one converges is that making some terms negative, let's write down what they are, okay? So if I have this guy, sum of 1/n, that's 1 plus a half plus a third, etc., right? Does that make sense? The alternating series that I just had, that ends up being 1 minus a half plus a third minus a quarter, right? And the fact that instead of adding on the 1/2 and 1/4 and the taking away of them instead is what makes this converge. But it's this kind of thing happening where the series, if you absolute value its terms, diverges, but the series with the negative in it converges, that produces all sorts of weird, crazy crap. Such as, and there's YouTube videos on this, you can YouTube it and look it up. You can rearrange these terms and the series doesn't add the same thing. Okay, so I thought this was crazy. Addition is commutative, right? As in you can change the order you add numbers. Unless you have an infinite sum and the series converges conditionally, then you can't. Okay, it's weird and we're going to talk about it later. Okay, yes?
So is that what Riemann's paradox is?
It could very well be. I don't remember that specific thing, but it's completely possible. I think that a lot of those arguments that like prove 0 is equal to a half or something like that involve rearranging the way they add stuff or commutative stuff in addition with things that don't converge in the first place. So yeah, I think probably, yes.
So then, for the AST, if one of the conditions is not met, does that mean it's not divergent?
We're going to do that one next. Okay. Yes, although it's technically not the AST anymore. So I listed those conditions in the box in that order for a reason, because it's always easiest to check if the limit is 0. And if that doesn't happen, your series is going to diverge. And by the limit of it, I mean the B sub n's, okay? So is this thing alternating? Okay, the series, well, let's just say alternates. That's faster, right? And what's your B sub n equal to? Over 6n squared plus 1. Limit. And just tell me what this limit is. Don't worry about doing the work. It's equal to a third, which is not equal to 0. Okay, so then, what can you say about the limit as n goes to infinity of -1 to the n? Is that equal to 0 then? No, that's going to be also not equal to 0. So the limit of the b sub n's without the negative in there is 1/3. When you add the -1 in there, it means that limit's going to flip-flop between positive and -1/3 eventually. Like you'll have this thing where as you go out to infinity, you're kind of going back and forth from -1/3 to 1/3, because as the n's get large, this thing gets close to a third. And the -1 to the n means every other term flip-flops positive, negative. And they're eventually staying 1/3 away. It's kind of like how the limit as n goes to infinity of sine of n does not exist, right? Why does that limit not exist? Because it oscillates, right? This is also an oscillating limit.
Okay.
Because the limits can't exist in a couple ways. They cannot exist because the limit's infinite, right? And they cannot exist because they don't make up their mind and go one place. This is one of those confused limits. It cannot decide where it's going. It keeps flip-flopping. I'm gonna live in Fairbanks, I'm gonna live in Hawaii, I'm gonna live in Fairbanks, I'm gonna live in Hawaii.
So in theory, is it have two limits?
Nope, it just doesn't have one. Just doesn't have a limit period. It just doesn't have one. I get what you're saying, it diverges in a different way. I totally understand that.
Right.
So technically, the series diverges. And it's not the AST, it's by the test for divergence. So you do have to specify that's what you're using. But officially, what Natalie was saying is like kind of right, that, you know, if that first condition of the AST isn't met, yeah, the series will not converge. But it's technically the test for divergence, that's the reason. No, once you do the test for divergence, you're good. Yeah, you start, what I would think, in my mind, I'm thinking, I'm gonna try to do the AST. Okay, I tried. I got, the limit wasn't 0 of the B sub n's, and therefore, by the test for divergence, this thing diverges. The series that diverges, that is. Does that make sense?
So they're similar enough that you can state both of them?
Yes, in some sense, but checking this condition, like that first condition not being met, this guy right there, that not being 0 will mean test for divergence, right? The limit of the terms with a -1 thrown back in there is also not 0. Okay. So this one. Okay, so is this series alternating? Yeah, the -1 to the n ensures that, right? Okay, so the series is alternating. I think I just spelled that wrong, sorry. Nating with, what's your B sub n gonna be? Over n cubed plus 1. Okay, check the limit as n goes to infinity of B sub n. How do you know this is 0? Power in the bottom is bigger. The technical way to prove it would be to either use L'Hopital's rule or divide by n squared, just to review this. That gives you 1 over n plus 1 over n squared. Does that make sense? And is it pretty obvious now that that limit's like 1 over infinity? Therefore 0? Okay, so that's 0. You can jump straight to that step in your work if you have to, because it really is you see that stuff in Algebra 2 classes, you talk about horizontal asymptotes usually. Okay. The next thing you have to show is that the B sub n sequence, or the B sub n's, are decreasing. And I maintain that it's not obvious, okay? Like, I'm just going to be a little bit picky about this. And my rule for it's not obvious, just to give you a specific rule, is that there's stuff in both numerator and denominator, so not as obvious, okay? And in that case, you have to use derivative, yep. So make a function. F of x is x squared over x cubed plus 1. And find its derivative using the fun, fancy quotient rule. If you want to YouTube it, there's probably a low-de high, high-de low to pop goes the weasel. I'm just not going to sing it. So low, which is x cubed plus 1. D high is 2x. Minus high, which is x squared. D low, which is 3x squared. All over low squared. So that simplifies to, okay, I won't skip any steps. 2x to the 4th plus 2x minus 3x to the 4th don't know about you guys, but if I skip steps, I just make mistakes. Do you have that same problem? Yeah, laziness doesn't win. Can you combine the like terms? So you have 2x minus how many x to the fourths? 1. And is there a greatest common factor there?
X.
X. Okay.
Do you have to do the derivative thing to prove that the big bottom is way bigger?
Nope, not even that. So you're trying to prove the sequence of B sub n's is decreasing. And you do that by looking at the function that's related to it, just as x instead of n. And you need to show that this function is negative. Because if the derivative is negative, then the function is decreasing, right? So when is this thing going to be less than 0? If x is bigger than some number. So first of all, do you agree that the denominator is always positive no matter what, right? So the numerator will be positive, either both terms are positive or both are negative. We don't care about if x is negative because our sequence only gives positive things, right? So if x is positive, how big must x be so that 2 minus x cubed is positive? X needs to be bigger than the cube root of 2. Does that make sense? Did I say, I think I might have said the wrong thing. If x is bigger than the cube root of 2, then 2 minus x cubed is less than 0, right? How about I actually solve that out and show you what I mean? So here's my step I skipped, which I really shouldn't have. 2 minus x cubed less than 0. 2 is less than x cubed, right? Cube root it all. Right? Okay. And if you're past that point, your x is bigger than the cube root of 2 is some weird positive number, right? Who cares what? Some weird thing. That makes this number positive, right? Makes this number negative. This number is positive. So the overall result is negative. Negative means the function was decreasing. And you can just say, thus, B sub n are decreasing. And what happens to your series?
It converges.
The series converges. By the AST. So when you have to use a derivative to show that the sequence of B sub n's is decreasing, what we're going to look for are a couple of things. We'll look for your derivative, and you have to show some work, not just Wolfram Alpha the thing, okay? The other thing we'll look for is, do you find the right point at which from that point on the stuff decreases, okay? And you can just do that by usually easy algebra solving. It won't even make a whole number line or anything. Just tell me where it starts to decrease. Okay. Yes?
So, as long as a point that where it's always negative exists, then
It's still going to converge, yep. And that's because you could just redefine, you could like leave the first, I don't know, 10, 100,000 terms off of your series and then just do the AST from that point on. And adding those first things you left off won't change the result. Yeah, but it's much like the integral test in that respect. As long as there's a point from which on the stuff, the B sub n's decrease, still converges. Okay, how about one? So this one is not obviously alternating. Does that make sense? Like it's not -1 to the n or -1 to the n plus 1. So verify for me or prove to me that you know it's alternating by telling me, is it equal to -1 to the n or 1 to the n? Let me see if I can answer the question while I'm teaching, okay?
Oh, this wasn't a question, I was just going to.
What do you think?
Yeah, I was just going to say that wouldn't cosine pi be negative?
Yes. So when you put in 1, cosine of pi is equal to
Guess that was a question.
-1. When you put in 2, cosine of 2 pi is equal to 1. When you put in 3, just in this top part, when you put in 3, cosine of 3 pi is -1. When we put in 4, cosine of 4 pi is, so is it alternating? And what I want you to do is rewrite that with a -1 to some power instead. And in order for your first term to be negative, and that is the case because when you input 1, you get cosine of pi, right? Should it be -1 to the n or -1 to the n plus 1? -1 to the n. Do you buy that? Okay. Is alternating. Well, hello. Sorry, just can't help myself with b sub n equal to 1 over n squared plus 1. Okay, limit n goes to infinity of those bn's. What is it? That's pretty obviously 0, right? Is this one of the ones where you can say they're obviously decreasing?
Yep.
Yeah, you could say b sub n is vousle decreasing as pn plus 1, which is 1 over. So the series does what? Converges. By AST.
That's a weird way to rewrite cosine.
Well, it's rewriting cosine at specific values. Do you guys see what I mean by that?
At only the integer values of n?
Yeah, at only the integer values of n pi, right?
Yeah.
Could I, it's a good question though, if I had just cosine of 2n, could I have rewritten that as a negative thing? No, it'd be cosine of 2, cosine of 4, cosine of 6, and those don't flip-flop in the same predictable way that the previous one did.
There's no pi. There's no pi.
Yeah, because there's no pi. So, no pi, no flip. So, since there's no pi, you can't make that conclusion with something like this, and we'll need a different test to show if I had that over n squared plus 1, that series would converge. It's not in this section, it's in the next section. Yeah.
If this, if you find out that series diverges by the, if it's not decreasing, would you say it's divergent?
Yes, and yeah, and I think in that case you could say by the AST. I think it also, that's probably also the test for divergence. I would need to think more about that because I'm pretty sure if your b sub n's are not decreasing, that means they're increasing or staying the same, right? And if they're increasing or staying the same, I think it's the test for divergence. So I think that if condition 1 is not met, if the terms don't go to 0, condition 2 will never be met, but I'm not 100% positive. Yeah.
So what if you want to test if we say diverges by AST?
You probably shouldn't say diverges by the AST, you only use AST for convergence. So the test you should use for divergence in this case will be test for divergence. It's just that it generalizes to flip-flopping things as well. Okay, about this one. Okay, so is it alternating? Okay, the series alternates. B sub n is equal to what? E to the 1 over n, okay. And then what you do is you try to apply the AST. I think that's what you guys are kind of asking questions about. Find the limit as n goes to infinity of Bn. Remember how limits can go inside continuous functions? So this can become e to the limit n goes to infinity 1 over n. So that goes to e to the, which is 1, which is not 0. Uh-huh.
That can be a problem.
That's going to be a problem, yep.
But what about the other bit there? The -1 to the end?
That's a great question. So what does, if the limit of just the positive bit isn't 0, when you add the -1 to the n in, is that going to make the limit 0? No. This is not going to be equal to 0 either. It flip-flops between -1 and 1.
Does that ever happen?
No, it never happens. If the, yeah.
Okay.
Yeah, no, so it will never happen that if you ignore the -1 part, if that limit is non-zero, putting the -1 back in means the limit is also non-zero. A good way to convince yourself, I just don't have the ability to do it in class right now, would be to take this guy and try to graph what happens as n goes to infinity. You can't graph it for all real numbers because like putting in like 1/2, you get -1 to the 1/2, which is an imaginary square root. But you could graph it for like values of n only, and you'll see that what happens as you go farther and farther out, with this specific example, your terms are they're flip-flopping between -1 and +1. They get closer and closer to that. They never get more spread out than that, but
That's what I was talking about earlier with the two limits.
that's what you were saying, yeah, the two limit thing. So, but a limit has to be one thing.
Yeah.
So, no.
So if it always means that the given series has a limit that's not 0, do we have to write that every time? Your then statement?
Yes, great question. Don't know the answer yet. Okay, because I have to just double check what Jill wants to do.
We have a promise to do it at 8 a.m. I said we have a promise to do it at 8 a.m. tomorrow.
You do, so for tomorrow at 8 a.m., write it both, okay? As for the rest of it, I think it's probably okay to just say the series diverges by test for divergence, but the test for divergence does technically say to check the original terms, not just the part, not the positive part. So on the take-home quiz due tomorrow, just write it for now. I'm sure that on the in-class quiz we could be more flexible just for forgetfulness. Okay. Tab. A little bit different. So series is alternating. What are you going to take to be your B sub n? N over e to the n. Same thing as n e to the -n. But I think for finding the limit of the B sub n's, it's easier to have it as a ratio. Because what rule are you going to use? L'Hopital's. And
Why do you have to use that when you have a polynomial over an exponential?
well, the reason a polynomial over an exponential always limits to 0 is L'Hopital's rule.
Oh,
Like, that's like really the reason why. And Jill didn't change her n's to x's, so I'm going to say you don't have to. That limit is 0. Do you buy it?
Yes.
Okay. To show decreasing, do you have to use a derivative this time? Are there n's in the top and bottom? Do you have to use a derivative? Yes, okay. So let f of x, I'm going to use the x e to the -x form because I think the product rule is a teensy bit easier than the quotient rule here. So how do you do product rule in this guy?
First times derivative of the second, but minus second times derivative of first.
Plus, otherwise good. So first times derivative of second, what's the derivative of the second?
E to negative.
Almost.
Negative.
Negative e to the -x. Plus second times derivative of first, which is, it's okay if you have those written in the opposite order, right? Okay.
No. Can you just ungroup them?
I was gonna take out an e to the negative x, if that's okay. So that's minus x plus 1. Is that all right? Or e to the negative x times 1 minus x. Is that okay? If you did the quotient rule, you should get the same thing. It's just gonna look a little different. You end up with 1 minus x over e to the x as long as you cancel correctly. So this is less than 0 if x is what? Greater than 1. Do you guys agree with that? Does the e to the stuff part actually matter?
It's always positive.
That's always positive. And 1 minus x will be negative as long as the x, the second term, is bigger than the 1. Like 2, 3, 4. Okay, so thus the series does what? Converges by the AST. Is that okay? All right. One more, then we're going to move on to something a little different. How about this guy? Converge or diverge? What do you think? Why do they think diverge? It's good. Yeah. So the flip-flops, but does the flip-flopping really matter in this case? Limit n goes to infinity of arctan of n. What's that go to? Almost pi over 2. Does that make sense? So the limit as n goes to infinity, throwing the negative 1 in there, is not equal to 0. I mean, if you want to...
It didn't go to 0, so it doesn't matter what that is.
So by what test? Test for divergence. This series diverges.
You ever get a thing where your negative term is also actually increasing?
I can't think of any examples off the top of my head.
Like negative 3 to the n or arctan n?
I can't think of anything off the top of my head. Like, it would require me to sit down and think. I have nothing to give you right now. I'd have to like sit in a corner and think, which is not a good thing to do in front of you guys. Yes?
If you have negative 3 to the n, can you say that that's negative 1 to the n times 3 to the n?
And then the 3 to the n goes to infinity? So test for divergence again? Yeah, no, exactly. If that's what I think actually happens every time, I'm just not. I just make no claim in front of people to it. All right, so here's the remainder thing. So the remainder theorem for the AST is awesome and super easy. It wasn't very hard for the integral test either, was it? Got that one wrong. So here's the AST remainder. If you have a convergent alternating series test, and I don't know why I switched to A's, let's change those to B's. Maybe yours already are B's. Are they? No, okay, well, change them to B's, because usually we let A sub n be the entire term, like in the series, and B sub n is just the positive bit. Okay. Then the absolute value of the remainder involved in estimating your sum by Sn is less than or equal to, I should say, capital B sub n plus 1, which is the next thing you leave off. And I should say B sub n plus 1. So if you add the terms of an alternating series and you use the first 10 things, the remainder is less than the B sub 11. Like the next thing you would have added on. But you just look at its absolute value, you don't care about its sign. Here's the picture. We're just going to prove by picture. 0, S2, S4. Remember that from the first page, right? Okay, and then up here we had S1, S3, S7, and they were all marching down to something S, right?
Why did we go from 3 to 7? Not like it matters.
Oh, 5. It should be 5. But I could have thrown 5 in the middle and then had left it as 7, right? Okay. So let's call this S sub capital N. Like I just decided to stop adding at some number. And then the next thing I do is I add a B sub capital N plus 1, right? Does that make sense? And that gives me the S sub capital N plus 1 next partial sum, right?
So despite the fact you decided to stop, you kept going just so you would have that?
Well, I decided to stop, and I want to figure out, so I stopped here and I want to figure out how far am I from S? Like what is that distance? And if I go over, if I added the next term, I would overshoot that distance, right? But would you buy that the absolute value of the error is less than or equal to that next thing? Do you buy that inequality? That's all this says. The absolute valuing allows you to be going like, if I had picked my thing up here and then went negative. But what it's basically saying is that, well, that distance from Sn to S is less than the next thing you add on. That's it. So if you add up the series of the first 10 things, you look at the 11th thing. First 100 things, look at the 101st thing. Super, super nice. Use it. Okay. So approximate this sum using the first 6 terms. So list out for me what S6 is. When I plug in 1, what's the first term? Yes?
Do we have to go through the steps of proving that it meets the requirements of the alternating series test first?
Technically, yes. I was jumping the gun. Did you buy that 0?
Whatever N was already 0, so...
For some reason, like, I think if I am going to ask for that, I'll be more explicit in the directions. Does that make sense? Like in this one, I didn't ask for it. You probably should make sure it converges by the AST, but it is definitely a really, really easy one. Example 8, if you look at it, it says show the series is convergent and then moves on. So just read the directions carefully. Usually I give you a really obvious one and the focus is the like remainder. Does that make sense? Okay. So if we are going to approximate S6, when you plug in 1, is your first term positive or negative? First term is positive, right? So we end up with 1. Do you buy that? But when you plug in 2? So minus 1 over 2 factorial. What happens next? Plus or minus? Plus 1 over 3 factorial, minus 1 over 4 factorial, plus 1 over 5, minus 1 over 6. That's about equal to 0.6319.
Going all the way to negative 1/6.
1 over 6 factorial, and 6 factorial I think is 720.
Yeah.
It's 6, 5, 4, 3, 2, 1, right?
Yeah, I did not mean to leave out the factorial.
It's a terrible joke if you make that number.
So the remainder is less than or equal to B sub 7. And what would have been my B sub whatever in this case? 1 over n factorial. So this is 1 over 7 factorial, which is 0.1230198. Is anybody a little bit amazed that we only added 6 things and we already have 3 decimal places of accuracy? Anybody else a little bit amazed by that? Slightly?
That may just have something to do with the powers of factorial.
It has to do with how quickly the factorial terms go to 0. Like, that's what matters, but it's kind of crazy. Okay, let's look at 8 quick. So the series alternates with b sub n equal to 1 over n to the 6th. This one actually said to show that the series is convergent, right? So then you should probably do that by the AST. You cannot do that by a p-series. Why not? Good question.
Positive.
Because of the positive negative thing. P-series is integral test. Integral test requires positive terms. Does that make sense? So that's the reason why. Do you buy that bn, what does bn plus 1 equal to? 1 over what? N plus 1 to the 6th. And how does that relate to 1 over n to the 6th? It's smaller. So our series converges. That part pretty easy, right? Okay, we want the error, which is less than or equal to bn plus 1, to be less than 0.12345 over 5. So what is b sub n plus 1 equal to? B sub n is 1 over n to the 6th, right? B sub n plus 1 is 1 over n plus 1 to the 6th. And let's write that as 5 over 1, 2, 3, 4, so 10, 100,000, 10,000, 100,000, million, right?
I'm going to cross multiply now.
We're going to basically cross multiply. Do you see what I mean? Multiply the 10,000, 100 million over, divide by 5, and you get 200,000 less than n plus 1 to the 6th, right? What do you have to do next to solve for n? 6th root. So 6th root of 200,000 less than n plus 1, and then minus 1.
It's fine to do it like that on the test.
On a test, yes. On the take-home quiz, I'd like you to get me a decimal for that. Does that make sense? But if it was like a test where you had no calculator, you could leave it like this. You end up with 6.647 bigger than n. So you have to round up. So n bigger than or equal to 7. Can I do one thing on example 9? Because it's a little bit tricky, but I don't want you to confuse. Okay, I'll hold you just 1 minute. So this is the same idea. You want the error, which is less than or equal to bn plus 1, to be less than 0.1234 and a 5. That's the whole 4 decimal places of accuracy. What would b sub n be in this case? 1 over 2n plus 1 factorial. So be careful when you input n plus 1. 1 over parenthesis 2 parenthesis n plus 1 factorial. Less than 0.00005. When you do those, when you like put the parentheses there and you simplify, what does that become? 1 over 2n plus 3.
All factorial.
All factorial.
So would you write that down to like 0?
Let me just do one thing. 20,000 less than 2n plus 3 factorial. How did I get that? I just cross multiplied basically, right? Does that make sense? Algebra. The kicker is here, there is no way to solve, as in there is no undoing a factorial. It doesn't work like that. So the only way to check here is to do guess and check.
There isn't like
And I'm-
modulus or something?
Nope, and I'm pretty sure and start kind of small, because it doesn't take many n's. Like, n equals 2 fails, but n equals 3 works.
Well, I always thought the reason for higher level math was so you'd never have to guess and check.
With some things, you still have to. So I apologize for that minor
N equals 3
snafu.
works, we would plug in, we would calculate S3 to get the,
When you plug in n equals 3, and you do that would be 9 factorial, it's bigger than 20,000.
no, but I mean, like, to get the answer to approximate the sum, we actually like.
You have to do
would do
S3. Yep, exactly.